Hi, everybody. This is the overview lecture to go along with assignment 22, which is about Leontief models. Um, Leontief models are a important concept in economics, and they make a great example, I think, of putting all the stuff we've learned about matrices and matrix algebra to the to solid use. They're very interesting in terms of seeing how matrix algebra can be used to understand a real issue. So let's get rolling. The first thing I want to do is have us look into the text area. Let's see. The the area we're in right now is section 4, and within that we're on the last subsection, 22 Leontief models. The let's open that up and look into the videos and readings things. And there's the PDF. So, but it did not open at the beginning. That was funny. All right, so here's the beginning of the section, and the history of this is sort of interesting. The Vasily Leontief created this way of modeling economic systems back in the 30s, and it was more than 40 years later that he finally got a Nobel Prize in economics for this work. It was really groundbreaking. There's two versions of it. The first one they call the closed model, and then there's, I guess it makes sense, the antonym of that would be the open model. In certain ways they're the same, but the closed model just assumes that we know what all the segments of an economy are. In the open model, there's an extra slot for sort of everybody else. Well, let's look at a closed model first, and I really like the approach they're taking here of just doing an ultra simplified thing. Well, I'll make a comment here that if you had a tiny little village with just three people providing all the goods, a farmer, a carpenter, and a tailor, and I suppose they're families, but you would probably have a sort of a communist arrangement where everybody just bartered, right? They just exchanged good for good. The assumption here is that we do have a capitalist system. We have money, and everybody gets paid a certain amount, and then they use their money to purchase the products from the other folks. But let's look at the input-output table. So if you read down the columns of this table, it's giving you the amount that's produced by each person, each segment of the economy. So we got somebody who's making food, the farmer, and their column is this first one. What's the rows? Well, that's the stuff that's being consumed by one of the elements of the economy. And so, for instance, this 0.40 or 40% is saying that 40% of the food that's produced by the farmer gets eaten by the farmer. It's produced, but also, well, funny, 40% also gets eaten by the carpenter and possibly his extended family. I guess the tailor has got a small family. I don't know. He only eats 20% of the farmer's output. Looking at the second column here, that's production by the carpenter. So that would include furniture and shelters, homes, maybe other things, tools made from wood. That's 40% of that carpenter's output is consumed by the farmer. 30% is consumed by himself. So he keeps 30% of his own output. And finally, 30% of his output goes to the tailor. That's what those numbers read. Similar thing for the tailor in the last column. Now, if you notice something about the columns of this matrix, you'll see that the numbers in every column add up to 1. In a matrix where the columns add up to 1 is called stochastic, and in this case we have a stochastic matrix column-wise. If the rows also happen to add up to 1, then we would say it was a doubly stochastic matrix. But these rows don't. And actually, that makes perfectly good sense. The stuff that's in the columns is all the production of each of the persons, each of the elements of this economy. And we're making a reasonable assumption that everything that gets produced gets consumed by somebody. Is there some reason why the rows would add up to one? Well, not really, if you think about it. The stuff that's in the rows, well, it's sort of an apples to orange comparison, right? We're saying 40% of the food gets added to 40% of the wooden products, added to 30% of the clothing. That, that sum doesn't make much sense. Of course, if you convert it to dollar amounts, it does make sense. But um, again, it's not reasonable to expect that that should add up to one. Some people will consume less than they produce, and some people will consume more than they produce. Well, is that fair to say? Probably not, because the actual way the input-output matrix gets used. Oh, well, before I talk about that, let's go ahead and see this table gets turned into a matrix in, I suppose, the obvious way. All right, so we have a matrix A that contains these numbers. Each of them is a positive number between 0 and 1. In other words, things that can be thought of as a percentage. Well, we're going to actually take, it calls it example 2, but it's just taking the same input-output matrix and putting it to use. Well, what is the use? We want to know how much each person in this economy, how much money they should get, right? How much should they be paid? How much should they receive for their production? And in the case of, well, in each of these cases, we make another simplifying assumption that they spend every penny that they make on other goods and services. Nobody's saving for the future. It's actually an unrealistic assumption, but it's not too far from the truth in primitive economies. You live hand to mouth. So nobody is saving for the future. Also, nobody's going into debt in a very small town kind of economy. There's no such thing as debt. People won't let you borrow overly much from them. So yeah, the idea here is that my outlays and my pay have to be identical. Now my outlays for the first equation that's given here is the one for the farmer. And it involves a weird thing here. He's 40% of his own pay, 40% of his own production is being consumed by him. So we see x on the left, but we see 0.4 times x on the right. Also, 40% of whatever the carpenter is producing is going to be consumed by the farmer. And finally, 30% of the clothing that's produced by the tailor is going to be consumed by the farmer. So this is called a linear combination. 0.4 times x plus 0.4 times y plus 0.3 times z. Those things total to whatever x is. A similar equation can be written down for what the carpenter gets paid and what the carpenter's outlays are. And same thing finally for the tailor and his outlays. When you put those three equations together, it forms a linear system where a vector, x, y, and z, is equal to a matrix vector product. The matrix is the IO matrix we just created, and the vector is the same vector that appears on the left. Now that means you can refer to that as x equals ax. And in one line they say simplification results in the system of equations I minus a times x equals 0. I think we need to say a little more about what that simplification is about. So I've pre-prepared some stuff. We start with that. X is equal to ax. Now, I personally prefer to write this in a slightly different way because the x's in that thing are they're called vectors rather than matrices. They're matrices with a single column. So we kind of like to decorate them in a different way so that we can tell those are single column matrices. So that's what we do. Put the letter for it and then put a kind of a vector arrow on top of it. So x is equal to ax, just changing the decorations from what's in the book. Now that is short for this whole system. xyz as a vector is equal to the result when you multiply our IO matrix times the vector xyz. Let me take that one slide farther. I guess I'll reveal this all a little bit at a time. We start with x equals ax, and I've made only one very subtle change here. I've got an I in front of x on the left side where it wasn't there before. I haven't made any change to the right-hand side. Now, what is that thing? Well, it's a matrix that is designed so that it has no effect at all on you multiply it times a vector. We're going to see specifically what matrix that is, but that's called an identity matrix, and it's for matrix multiplication, it acts sort of the same way 1 does for regular multiplication. You know, if you multiply 1 times some number, you just get that number. It doesn't change anything. Well, if you multiply I times some vector, it doesn't change that vector. All right, so what happens next? We take the thing on the right-hand side and subtract it from both sides. So it goes away on the right. That's why, I'll come back to that in a second. On the left, we've got ix minus ax. On the right, okay, this is coming back to it in a second. You've got a vector that contains zeros. See, both of these things are actually length 3 vectors, single column. They're 1x3 matrices when you work out their sizes. And when we subtract them, we'll get a 1x3 matrix, but it's supposed to be 0. It's not truly the number 0, it's a matrix that's 1x3 that's full of zeros. That's how you denote such a thing. Okay, the last step in getting us back to what's in the book is just the distributive law. Matrix multiplication distributes. So I guess we could think of this as the opposite of distribution. We're factoring out the x on the right. So I minus a is one thing, and that times x gives us a 0 vector. All right, so I think we're now ready to see all of this in practice. Actually, let me pop back to the book for 1 second, and then we'll go to GeoGebra. What they've written right here in the book is the thing I minus a times xyz, that vector x, is equal to all zeros. And they just use the Gauss-Jordan method, and they get a solution. I think we should pop over to GeoGebra and see some more detail about that. All right, so in GeoGebra, which I have open already, we're in the CASP menu, so the CASP version of the calculator, so it's going to not really graph anything. So I'm almost zeroing out the size of the graphing area. We won't be using that. I'm going to do this in a couple of stages. Well, the first thing is the first thing I should point out is you guys should do this too. Do a little bit of setting up. There's a settings area in the global menu there. If you have GeoGebra in its stock form, it gives decimal answers to 13 decimal places, which is, I mean, I guess it's nice to have that kind of accuracy, but it's a little off-putting because in real things, you very rarely know things that accurately. So I'm going to reduce it to 4. 3 probably would be more accurate. I'm also going to, just for the sake of us being online and I want to display things well, I'm going to set up the font size on this thing to be pretty huge so that you can see what's going on screen. All right, so let's first put in the matrix that represents that IO system. Remember, use French braces and comma-separated lists to do your matrix entry. So let's see, my first row of the IO matrix was 0.4, 0.4, and 0.3. And the second row is 0.4, 0.3, and 0.2. And then finally the last row, the third row, is 0.2, 0.3, and 0.4. That's the matrix A that was given in the textbook. I don't like what GeoGebra, well, maybe I do. This is turning everything into actual fractions because it could. And that means that's numerically accurate. I prefer a decimal approximation, which in this case is no different because the stuff was input as decimals. But if there were, you know, actual fractions involved, we would be now seeing these to 4 decimal places. That's our matrix A. Now the matrix M we really want is, the coefficient matrix anyway, is I minus A. You need to get yourself an identity matrix, and maybe this is a good time to show you what an identity matrix really looks like. Notice that the search ahead, the typing ahead thing gives us a chance to input that command. Just type ID and it jumps out at you. It's asking for a number here. Identity matrices are always square, so this number is only a single number is required. You don't do like 3 by 4 or something, because there wouldn't be an identity matrix of that shape. But a 3 by 3 identity matrix is good, and it'll look like that. Now, if you think about what a matrix like that has ones on the diagonal and zeros everywhere else would do when you do matrix multiplication, try to work through that on your own. But shortly you should realize, oh yeah, that's not going to affect whatever I have as the vector. If I have XYZ as the vector that's right next to this, when I do the multiplication, I'm going to get a vector that looks like XYZ. For us, we need to find the matrix where we take that I and subtract the reverse thing that I put in, I minus A. And again, I like to see it in decimal form. Now, you could do this if you wanted, but I find that I can do it myself rather quickly. And so there's no point in actually creating an identity matrix and then doing this subtraction, because you just need to look at what happened to stuff, and you'll be able to figure out what to do. So what did happen to stuff? Well, the numbers on the diagonal, notice how they're all positive. Those things come from these ones minus these numbers. And so like the 1, 1 entry is 1 minus 0.4. That's 0.6. You could do that without having to actually get the computer to do the subtraction for you. Stuff that's off the diagonal just comes from the matrix A, because that's stuff where you have a 0 minus an entry from the matrix A. So like the 1, 2 position of A was a 0.4. The 1, 2 position of the identity matrix is a 0, and that makes this position 0 minus 0.4, or negative 0.4. So most of the entries of this matrix, you just take them out of the matrix A, the input-output table, and throw a minus sign in front of them. But when you're on the diagonal, do 1 minus. Okay. It's going to be convenient, or I think more than convenient, it'll be useful to be able to put in these kind of matrices, just do it yourself without doing the subtraction, because you also need to throw in an augmented column. Now let me pop back over to the DocCam view for a second. What is the augmented column here? We have this matrix that I minus A that I just came up with for the coefficients, but this right-hand side is supposed to be the augmented column, and it's a vector full of zeros. So that's super easy to put into. All right, so now I'm going to work with the same system, but put it in directly. Okay, so here we go. M is going to be a matrix. This time it'll be a 3 by 4 matrix, meaning list of 3 rows, but there'll be 4 entries in each row. As I said, well, actually, I've got the coefficient matrix right above me, but let me just kind of think and talk through the process for you. The 1, 1 entry is a 1 minus the 0.4 that came from the input-output matrix. And so that's going to be 0.6. The other entries come from the input-output matrix, except they have a negative sign in front of them. And the last entry comes from the augmented column. It's got a 0. Now I need the things for the second row. The 2, 1 position is just a negative, whatever the entry was from the input-output table, but the 2, position is that 1 minus bit, so you get 0.7 there. Negative, oops, wrong key, negative 0.2 there, and finally a 0 in the augmented column. And then last row, that goes, well, you can see it right above us here. So it's minus 0.2, minus 0.3, 0.5, and 0. And again, I think I prefer to see the decimal version of that. Just click on that. If you click on that twice, you go back to the fractions, by the way. Okay, so that's, I'm just double checking, but that's correct. You see it's got the right shape, positive numbers on the diagonal, negative numbers off the diagonal on both sides, and then a column of zeros in the augmented position. Let's get the reduced row echelon form of that. Okay, and we want the reduced row echelon form of the matrix I called it. Once again, let's take that as a decimal. Here's where you see the, I mean, if you look back at the fractions, they have 13 and 26 in the denominator, so they're not particularly nice, and the decimals rounded to 4 decimal places is pretty reasonable. Now we've got to look at that reduced row echelon form and recognize it as the solution to a system. There's 2 basic variables, x and y are basic. There's a whole row of zeros, which means it's consistent, right? We don't have a 0 equals something non-zero here. But what does that tell us? That there's 2 pivot positions, and there's a column that represents a free variable. It is z is a free variable. X and y can be expressed in terms of z. Now, so for instance, this top row says x minus 1.11 times z equals 0. And you could just move it to the other side. You get that x is 1.11 times z. Y is 0.923 times z, and z is free. I'm gonna switch back to the dot cam for a second, and we'll just write that solution down, because let's see if I can manipulate my screen so I can see the numbers again. So we have an answer where apparently I used a different pen last time. Anyway, x is 1.114. I rounded it wrong. 115 times z. Y is 0.923 times z. And z is a free variable. If you like, you can do this in that alternate form where we come up with a name for the parameter. So then you have x is equal to, let's say, 1.115 t. Y would be 0.923 t, and z would be t. We can kind of, I don't know, personally I actually kind of prefer that way, naming the free parameter a little bit. So what does this say to us? Well, remember what these were. These were the amount that people were paid. And if the economy is perfectly balanced, where everybody is, getting a fair deal, they're receiving for their efforts exactly what they're putting into the system, or what they're getting out from the rest of the economy, then what we've got in this case is the tailor should be used as sort of the baseline. Z is T. Whatever he makes, the carpenter should be getting 92% of that. And the farmer should be getting a bonus above that, 1.11 times that amount. So if you in a certain sense, the amounts of these things are arbitrary. If the tailor's pay was $100, then the carpenter would be getting $92, and the farmer would be getting $111. Just have to scale it according to what the money is worth, what the value of money is worth in this economy. Well, that's a pretty good example of the closed system in a Leontief model. Let's pop back over to the book and have a look at an open model. Oops, that's GeoGebra, not the book. So, all right, yeah, the open model. Well, what this does is creates the same thing as before. We have a bunch of production and a bunch of consumption. But then there's this additional thing, this sort of sector that represents everybody else in the economy. So they changed things. No, they didn't. They kept it farmer, carpenter, and tailor. It's fine. F, C, and T are the names for those folks. But then there's consumer demand for each industry in billions of dollars. And it's given by, well, billions of dollars. These are very productive farmers, carpenters, and tailors. Anyway, 40, 50, and 60 are the numbers. Okay? So how does things change? Well, in the closed model, remember what we had before? No, can't seem to highlight that properly. X equals AX led us to get the solution. Now we have the idea of consumer demand. So that gets added to the outlays from each group. So like the pay for the farmer would be what he gets from the other things plus the money he gets from the consumers. All right. Here it is laid out in full form. You write it in a abbreviated way as x equals ax plus d, but well, we've got a coefficient matrix there that represents the intersegment demands or intersegment production and consumption. Then we've got consumer demand out on the end. Yeah, all right. Let's see if we can work the algebra the same way. We started with x equals ax plus t. Subtracting ax from both sides and factoring it out, you get I minus a, just like we had a minute ago, times x. That's now on the left-hand side. And then d is what remains on the right-hand side. That is, we will have an augmented matrix that is no longer a column of zeros. That's known as a homogeneous system. It's all zeros. We've got numbers on the right-hand side now that correspond to our consumer demand. You'll notice also the matrix. Well, let's go back to the matrix A here. Is this stochastic anymore? Remember that meant the columns added up to 1? Not at all, because the production is not just going to the members of this small village anymore. There's the consumers outside of the village that are getting lots of stuff. So yeah, only we have about 45% is stuff that goes in, it's traded in between the different elements of the consumer, the producers in this economy. Yeah, all right, so let's just follow the algebra now. What we need to do is make well, I think this is perfect. Well, no, I don't think we want to jump into example 4 just yet. Let's do example 3. X equals ax plus d. This will become a non-homogeneous system where I minus a times x equals d. No, oh, that's right. They're doing something in the book that actually is smart, but I'm not going to do it. They create what's known as the inverse matrix for I minus a, and they multiply both sides by I minus a. Excuse me, I minus a's inverse. That means, because it's an inverse, it's like multiplying 1/3 times 3. They just knock each other out. And you can compute in GeoGebra the inverse of a matrix, but I find it's just simpler to create the coefficient matrix and the right-hand side, and then do row reduction to get our answer. Because that's something we've already done. Why throw this new wrinkle in it? If you're interested in figuring out how to calculate the inverse, I can do that, and then I guess I should do that just at least once, and then we'll skip it and do row reduction for our solutions from here on out. So let's take this system, pull it out there so I can just out of my picture so I can copy the numbers into GeoGebra. But you're seeing the right stuff there. Actually, I'm also going to just clear out what we did previously on GeoGebra. Let's discard the changes. Okay, so the matrix A for inputs and outputs is 0.2. I'm again just copying out what was in the book. 0.25 and 0.1. That was the first row. The second row is 0.15. Whoops, gotta make a comment in there. 0.10 and 0.05. And then the third row is 0.1, 0.05, and 0.15. Yeah. Didn't let me finish that, so I'm worried that I've got an error in the way I typed it. I'm just double checking that nothing, no commas got left out or anything. It's fine. Needs an extra, needs a close parenthesis that it's not letting me do. Oh my. Oh, I see what happened. All right, so to fix that, we're going to have to go to settings and see how that was defined. Somehow I thought there was an if in there. Maybe I just typed something wrong. And it's got a logical symbol in there instead of a comma. I don't think I typed that, but there it is. Okay, try it again. That's, by the way, how you deal with it if you type something wrong in there. Go back into settings, find how it was defined, and then fix it. All right, again, it's written it as all in fractions now, but we can get back to the decimal approximation if we like. The matrix that we need the inverse for is an identity minus this thing. So let's call that M like we did before. I'm going to take an identity matrix of size 3. And I'm going to subtract the matrix A from it. Okay. Oh, that's because I never named this thing. There we go. Notice this did what more or less what we saw before, where you got 1 minus numbers on the diagonal, so they end up being positive, and then the negatives of the entries from A are off the diagonal. Let's do this inverse thing. Well, if you just raise it to the -1 power, that's one way to do it. And wow, it's going to be some ugly decimals in it. But it's a matrix that if you multiply it, oh, darn it. I should have named it. How about M sub I? I want a name for that matrix so that I can use it in another line. But yeah, it's a matrix that, look what happens if I times multiple this M sub I times the original matrix M. It comes out an identity matrix. This is really just like something like 1/2 times 2 equals 1. It's just the matrix version of that. Okay? So that's a way to approach our stuff, but I'm not going to advocate for doing that inverse matrix process. Instead, I'm going to advocate for us writing down the M minus A part in the coefficient matrix, and then putting the 40, 50, and 60 that were on the right-hand side into the augmented column and using row reduction. All right, well, let's give it a go. Need a new name for the matrix, so I'm going to go with P. The first row of this P matrix is going to be 1 minus what was in the augmented matrix. Can I get back to showing you the augmented matrix for a second? I said augmented matrix. Pardon me for that. I was trying to say, what was I trying to say? The input-output matrix, the I/O matrix. So that had a 0.2 in it. I minus A is going to have a 0.8. That's the numbers I'm going to want to copy into our thing, the stuff that says I minus A in the book. All right. All right. So 1 minus 0.2 is 0.8. And then we have negative 0.25, negative 0.1, and the augmented column was 40. I hope I'm remembering that right. 40, 50, and 60? Yeah. Oh. It's doing this thing which I really despise, where it changes my input to something else. I'm going to just zero that stuff I put in there out, and then we'll hopefully be able to put it back in properly. Do need those commas when you put them in. Oh, it's done it again. I wonder if I can. Oh. All right, you know what? I think I want to just clear out this particular guy. I can't do it, can I? There. Delete. There we go. Let me just start fresh, because that sometimes it's frustrating. All right, let's try again. 0.8, comma, negative 0.25, comma, negative 0.10, comma, 40. Next row. There we go. Negative 0.15. The second entry in the second row is the place where you're going to be 1 minus the entry. So we get 0.9 there. Then a negative 0.05. And the augmented column contains a 50 there. And in our last row, it's negative 0.10, negative 0.05, negative 0.85. Why the no, not negative, positive, because this is the 3-3 position, so that's the 1 minus part. And we need something in the augmented column for this guy. It was 40, 50, 60, yeah. All right. Looks good. I think we've done the right thing. I'll put it in decimal form so we can verify we've got the shape we want. Negative numbers off the diagonal in the coefficients. In there. Numbers that look like 1 minus something in the, yeah, and our augmented stuff. Cool. So that's our matrix that we need to row reduce. Reduced row echelon form for the matrix P. Now this, what is this? This is a 3x3 matrix. The reduced row echelon form has 3 pivots in it. The stuff on the right-hand side is the free column. That is, it's telling us what the values of these pays to the various sectors should be. This one is saying X is 83.8. I'm rounding the rounded thing already. Y 74.2. These are numbers that are expressed in terms of those consumer demands for the products and the things, but I'm worried about the scale of these numbers. It seems like the producers are making more than the consumers are demanding. I could just check this by making sure that the inverse matrix for our thing times the consumer demand vector. What happened? I accidentally hit go. Check 40, 50, and 60. Yeah. Oh, those are different numbers. Wow. Well, I guess I better stop there and say, let's do it the way the book says. These numbers are and they're considerably different from what my do in reduced row echelon form. I really cannot see why. I'm going to have to come back to this and try to explain why these results didn't come out the same way, because they should have. But, well, okay, so this will do for now. You find the matrix that looks like an identity minus your input-output thing, call it something. Find the inverse of that matrix, and then you times it by the demand vector, 40, 50, 60. And this gives you the pays that should go to each of the different sectors. At least I was concerned that these numbers add up to more than the consumer demand in dollars, but that's ignoring the inter segment demands, right? Like the farmer didn't only have $40 billion worth of stuff coming from consumers or being purchased by consumers, but he had some other stuff that was being purchased by the carpenter and the tailor, and so that's why it adds up to more. Okay. Well, that's probably a terrible place to stop, because I've left you with an unknown why the row reduction method didn't come out the same as the inverse matrix approach. But since the inverse matrix approach is what's in the book, I'm thinking I've got some subtle error in my thinking about row reducing, and I'll probably have to come back to you in the video lecture for the overview lecture for the next assignment with a quick explanation of where I went wrong here. Oh, well. Sorry for that. But I think that's a good place to stop. So let's have a good rest of your day. Hey, it's me again. I just couldn't take it. That was really bugging me that the two different methods didn't come out the same. So I played with it a little bit and realized what the issue was. It was stupid. It was just typos. I had put in the matrix A completely wrong, but here's the matrix A as it's supposed to be. A is, well, yeah, those numbers. And the identity matrix minus A looks like that. When we find its inverse, it looks like this. I checked that it's still the inverse. When you multiply the inverse times matrix M, you get an identity matrix. The calculation of P was the one that actually worked out right before, and that's what we got for the reduced row echelon form. Now that MI is correct, the inverse matrix for M is got the right numbers in it. Times that times the vector with 40, 50, and 60 in it, you get exactly the same numbers that you see in the reduced row echelon form of matrix P. So either method will work. I do prefer the row reduction, and it turns out, maybe with good reason, it gave me the right answer this time. Honestly, they're both about the same amount of work, but anyway, just had to let you know about what was up with that miscue before. All right, now really have a good rest of your day.